The second question here, my friends, is a little tricky question, which is not going to be very easy to understand in the first place. But I mean, you need to be very careful about it, because the next question, question number 3, is going to be even harder than this one. So better you better understand this question in the first place. So imagine there is a party, and in that party there are n men. N men. They throw their indistinguishable hats into the center of a room. So they are throwing their hats, but their hats are all the same, except, let's just say, inside the hat, the name of the owner is written inside the hat. But when you throw them in the middle of the room and mix them up, you cannot select your own hat without looking at the name. Okay? So they are throwing their indistinguishable hats, which are all similar, and they are mixing up these hats, and each man randomly selects one hat. Okay? So the question is this. We know that some of these men will be lucky and will select their own hats, and most probably most of the men are going to select each other's hats. Okay? But of course, it is possible that there may be some men to select their own hat. So the question is asking me this. What is the expected number of men who select their own hats if there are n men in the room? Okay? So let me give you an example to that. Imagine n is equal to 1. So there is just one man. One man is taking his hat off, throwing in the middle of the room, and selecting it again. What is the expected number of men who select their own hats? It is going to be 1, right? Exactly that man. I mean, this number is not going to be random at all. We know that there is only one man here. Now imagine there are 2 men inside the room. 2 men. So when they throw their hats and mixing them up in the middle of the room, in the center of the room, either in the end of this process, either they are going to select each other's hats or they are going to select their own hats. So with 0.5 probability, the number of men who select their own hats will be 0. With 0.5 probability, the number of men who select their own hats is going to be 2. And therefore, the expected value here is going to be equal to 1. Okay? So if there are 2 men, the expected number of men who would select their own hats will be equal to 1. Because we have either 2 or 0 with respective probabilities of 0.5. Now, what happens if we have 3 or more men? Let's just say we have n men. Okay? So in order to solve this question, I am going to use Bernoulli random variables and the concept that I have learned just a moment ago, the sum of expected value of the sums of random variables. So let's just say x is a random variable which denotes the number of men that select their own hats. And the question asks me to compute the expected value of x. So imagine now, I am defining n different Bernoulli random variables and different Bernoulli random variables for each man. So how do I count the number of men who selects their own hat in the end of this procedure? Okay, so imagine the procedure. In the end of this procedure, I will one by one ask each of these men if they have selected their own hat or not. Okay, so I will ask to the first man, did you select your own hat? If he says yes, then x1 is going to be 1, and it is going to be counted towards the number of men who select their own hat. But if he says no, I couldn't select my own hat, then I will say x1 is equal to 0, and it will not be counted towards the total number of men who selects their own hat. And I will ask the same question to the second man, to the third man, to the fourth man, so on and so forth. So for the man who answers yes, I am going to take the respective Bernoulli random variable as 1. Otherwise, the respective Bernoulli random variable is going to be 0. Of course, the sum of these 0 and 1 values for n men is going to be equal to the total number of men selecting their own hats, right? So therefore, actually, that x value, which is in our interest, is the sum of n Bernoulli random variables, and each of these Bernoulli random variables take the one value if the respective men selects his own hat. Okay. Now, let's analyze these Bernoulli random variables. So what is the probability for any man to select his own hat? Or in other words, what is the probability of xi to be equal to 1? So what is the probability of the ith man to select his own hat? Now, actually, it depends on the selection of the previous man, right? But, I mean, if imagine you are the first man to select, what is your chance to select your hat, the correct hat? If you are the first man to select, it is 1 over n, right? Now, you should not think in the order of time, and everybody here is selecting one of the hats, right? So everybody has this chance, the same chance of selecting their own hat as 1 over n. Okay, even the last man who selects his own hat has the chance of 1 over n. Why? Because if nobody selects his hat, the last man can also select his hat with 1 over n probability. So what is the probability for nobody to select the last man's hat? It is again 1 over n. Okay. So if you think from the hat's perspective, not the man's perspective, if you think from the hat's perspective, the last man's hat to be the last one in the middle of the room, remaining in the middle of the room, it has the chance of 1 over n. So any man selects his own hat with 1 over n probability. Now, maybe you can get confused. I'm not saying that these random variables are not independent. They are obviously dependent. For example, if the first man selects the second man's hat, then x2 is going to be equal to 0 with 100% because his hat is already selected. But there is a chance also that the first man does not select this guy's hat. Therefore, everybody has the same chance about selecting their own hat, which is 1 over n. But these random variables are dependent. But you know that our objective is to calculate the expected value of x, which is the expected value of the sum of these Bernoulli random variables and Bernoulli random variables. It is going to be equal to the sum of individual expectations, whether these xi values are dependent or independent. It doesn't matter. Therefore, all I need to do is to calculate the expected value of each xi with Bernoulli random variable success probability being equal to 1 over n. And the expected value of a Bernoulli random variable is equal to 1 over n. Well, actually, the success probability p, which is 1 over n in this case. Therefore, when you sum up n 1 over n values, you are going to get 1. So independent of the number of men inside the room. So even if you have 1 man, or 2 men, or 3 men, or 4 men, of how many men would you like? The expected number of men who select their own hats in this procedure is always going to be equal to 1, independent of the number of men inside the room. Okay? Actually, we have tried it for 1 and we have tried it for 2, and the answer was true. I mean, for generally speaking, if there are 10 men or 100 men inside the room, again, the expected number of men who select their own hats is going to be 1.